Okay. I hope my voice is audible now. Okay. Good evening, everyone. I am Somnath Hazra, a PhD scholar from IIT Kharagpur, and this is your 7th week on CS100 Operating System Fundamentals NPTEL live session. So every week on Tuesday at 6 we conduct sessions like this for 12 weeks of the course. So this week we will be discussing some problems on synchronization. So let's start the session. Okay, I hope the my screen is visible and my voice is also audible. So okay, if you are facing any problem, feel free to use the chat box. Okay, so this is the first question. Which of the following conditions must be satisfied to solve the critical section problem? Mutual exclusion, progress, bounded weight, or all of the above? So which among the following conditions is a requirement for critical section problem? So anyone with the answer may use the chat box. Okay, I got one answer. Anyone else would like to contribute? Okay, I got two answers. Anyone else would like to contribute? So for those who joined just now, the problem is that which of the following conditions must be satisfied to solve the critical section problem? Mutual exclusion, progress, bounded weight, or all of the above? So which among the following do you think is correct? Okay, I'll go to the solution now. Just give me a second. Okay, this is the solution. So yeah, actually all are correct. That is, mutual exclusion is also a required condition, progress, and so is bounded weight. So all of the above is the correct option. So anyway, what are these three? So mutual exclusion, as you may know, is the primary requirement of the critical section problem. Just give me a second. Yeah, so mutual exclusion is the primary problem of the critical section. That is, when you are in critical section, the necessary requirement is that only one process exists in this section, because here you are working with shared variables, and multiple processes accessing the critical section or accessing the shared variables may result in incorrect results. Like race condition and so on and so forth. So for that case, the critical section is specially designed with an entry section and an exit section, and so that only one process can get entry into the critical section and then perform the required operations on the shared variables, and then it signals that its operation is complete, so that the other processes also get a chance. The other processes that are waiting for access of the critical section. Okay, so this is the common idea. So mutex satisfies just that. So it only allows only one process entry into the critical section, and yeah, that is the foremost requirement. The other two requirements are progress. Like what progress means is that if no process is there in the critical section, and if some new process comes forth and wants an entry into the critical section, then deciding which among the waiting processes should get into the critical section, that should not take very long, that should not take indefinite amount of time. There should be progress in the decision making, that which process goes next into the critical section if no other process is there in the critical section, right? So that is what is meant by progress. Bounded waiting means that there should be a bound on the limit on how many times a process is denied entry into the critical section after it has made a request for doing so, right? So what that means is that suppose there exists a process P1 that has requested entry into the critical section, but due to priority scheduling or some other reason, it is never getting an entry into the critical section, and some other process is always and it is always interrupted in between, and some other process is executing into the critical section always. So for that, so that results in a problem which is so that is a problem, right? For because the process can't progress, so with its execution in the remainder section also. So that is what results in that. To avoid that, the bounded waiting condition must be satisfied by the algorithms that aim to solve the critical section problem. So the requirement that is specific to the critical section problem is the mutual exclusion, as you may have understood. The rest of the two requirements are specific to the process. So yeah, the shared variable, the security of the shared variable is ensured by the mutual exclusion principle. The other two just ensure that there is the processes get a chance to enter into the critical section and progress with the required job. Okay, so yeah, these are the three requirements. Actually, the mutual exclusion and progress are the two primary requirements. Bounded waiting is a secondary requirement. Okay. Because there are various algorithms to avoid bounded waiting pretty simply. So it is a secondary requirement. So even if there are algorithms like that satisfy the mutual exclusion and the progress requirements, so they are also accepted solutions. Okay. So yeah, another requirement is architectural neutrality, but that is given always. Like the architectural neutrality, as the name suggests, is that the solution should be independent of the architecture on where the solution algorithm is running. Okay, so yeah, there are various computer architectures, as you may know. So it should be independent of the computer architecture. So that is it. Let's move on to the next question anyway. So in a critical section, more than one process is allowed to enter into the critical section. No other process is allowed entry into the critical section when one is executing in the section. Several processes can access and manipulate the same data concurrently, or none of the above. So which among the following do you think is correct? These are correct. Anyone would like to contribute? Okay, immediately get an answer B. Anyone else like to contribute? Waiting for answers. So I partly discussed actually the answer in the previous slide. Anyway, I got two answers. Anyone else would like to contribute? Anyway, let's go to the answer then. Yeah, it is B. That is the critical section problem. That is the only requirement of the critical section problem, since it contains the shared variables. it should not allow any other process into the critical section when one is already there. Okay. So this ensures that there is no race condition, as you may have studied in the theory. So what race condition means is that if any process gets hold of the critical section, so it changes a variable. So the process that enters first into the critical section, that process has the foremost right to change the critical section, and the process that enters last, that has the most significant impact in the critical section variables. So I am not going into the details of that. I need much theory to explain that part, the race condition part. Anyway, let's progress with the next question. So concurrent access to shared data may result in data insecurity, data inconsistency, data consistency, or none of the above. So which one do you think is the correct option? Okay, I get one answer. Okay, two answers. So I'll wait for 4 or 5 minutes. Yeah, I get another answer. Yeah, anyone else? So what data insecurity means is that data is not securely stored. So security is not what we are studying here. Consistency means whatever copy of a variable that are there in many, so there may be shared variables among many processes. So all the local copies of the data that are there in, with all the processes, they have the same value of the variable. Suppose there is a variable A that is shared among many processes. So all the processes will will have the same value of A, can see the same value of A. So that is what is meant by data consistency. So concurrent access, what do you mean by concurrent access is that multiple processes can enter into can share the can have access to the shared data, and what that does is that it changes, so multiple processes can change the data in an incorrect manner, and since there is a since there is a problem of which process gets scheduled in the CPU, so that may lead to inconsistencies. Since you know that changing a data or access to the data or writing a data, it is not a one-step process. There are multiple steps involving bringing the data into the registers, then making the change, suppose addition, multiplication, subtraction, things like that, or things like that, and then putting it back into the putting it back from the register to the storage location. So that is a multi-step process. So you might have read in computer architectures that there is this fetch, then decode, then all those instructions are there. It is a 4 or 5 step process. So that and context switch in between that may result in data inconsistency, right? So concurrent access results in data inconsistency. So that is what we are trying to solve with synchronization actually. That is the whole problem. Yeah. So let's move on to the next question anyway. Peterson's solution works with how many processes? many 1 sorry 0, 2 or none of the above. So yeah, okay, I got one answer. Anyone else? Anyone else would like to contribute? Okay, I got 2 answers. So I'll wait for another minute. Okay, let's move to the answer. So yeah, it works with 2 processes. Okay, so what Peterson's solution does is it has 2 variables, flag and turn, as you might have seen from the lecture slides. So what that does is it checks whether the other process it wants entry into the critical section or not, and then provides the turn to the other process. Yeah. So in the entry section of the algorithm, what it does is that it first raises the flag of its own and says that it wants entry into the critical section, and then gives the turn to the other process. Like two processes are executing parallelly, right? So it gives the turn to the other process and says, and then it checks if the other process needs entry into the critical section, and if the turn is with the current process. So if those conditions are satisfied, then only it goes enters into the critical section, otherwise it cannot. So yeah, the problem is that it can work with only 2 processes. We'll talk about more about that later. So yeah. Anyway, next question is, Peterson's solution requires dash variables and is a dash based solution. So what is your answer to this? Does it require 2 variables and is a software based solution? Does it require 1 variable and is a software based solution? Does it require 2 variables and is a hardware based solution? Or does it does not require any variables and is a hardware based solution? Okay, I got 1 answer. I got 2 answers. Anyone else? I got 3 answers. Anyone else? Okay, wait. Let's move to the solution. So yeah, Peterson's solution requires 2 variables, as I was describing, and it is a software based solution. So yeah, there is no hardware requirement as such, so it can work with any hardware. So yeah, so this is the critical section. Okay, so yeah, this is the critical section algorithm, so Peterson's algorithm actually for the critical section problem. So as I was saying, so this what is shown, what you are seeing right here is the process I, is for the process I, and there is another process J. Okay, think of that like that. So these are the 2 variables, flag and turn. So what process I does is that it first raises its current flag that it wants entry into the critical section, and then gives the turn to the other process J, right? So if there are more than 2 processes, there is a confusion about who will this process give turn to. So that is the problem. If there is just one other process, so there is no need of selection, it just can give the turn to the other process J. Okay, and then what happens is that it checks if the other process also needs to enter into the critical section and if it currently has the turn. Okay, So if both the conditions are true, then only it will keep waiting. So semicolon here means wait, it will not enter. Okay, that is why the semicolon is given. So it will keep waiting in this line only. Okay, so think of so suppose there is no other process J. So in that case, what will happen? This condition will be false, and it will get entry into the critical section. So although turn variable is set to J, but this condition is false, so it will get entry into the critical section. And suppose there is another process J which wants entry to the critical section, and so that is also executing parallelly. So that will have a line like turn equals to I in the entry section. So there also so after the so suppose that after execution of these two lines, there is a context switch to that process J, and there also the same two lines are executed, and there is again a context switch. So what happens after that is that the flag, although the flag is raised by the process J, the turn is not J now, the turn is I. Remember, in the other process what happens is that in the process J, the turn variable will be set to I, right? So so this condition is not satisfied, so it does not need to wait, so it can get entry into the critical section. Okay, so yeah, after it has finished execution, it switches off its flag, and then it can go on to the remainder section. Okay. Yeah, so this is the Peterson solution. Let's move on to the next question. So what are the drawbacks of Peterson solution? Is it busy waiting? Is it that it works for two processes only? Is it that it does not solve the progress requirement, or all of the above? So which one do you think is the correct answer? There can be multiple correct answers. Okay, I got one answer. So what are the drawbacks of Peterson solution? Okay, I got two answers. Anyone else would like to contribute? Okay, before going into the solution, let's get back to the algorithm first again. So what mutual exclusion says is that only one process will get entry into the critical section. So that is obviously satisfied, because either process I or process J will get entry into the critical section. Okay, now the other requirement is that it progress. So what happens in progress is that if no process is there into the critical section, then there should be a finite time selection among the waiting processes for the critical section, right? So the so obviously after some time this it will come to this line for both the processes I and J, and only one process will get entry into the critical section. So either process I will be waiting, process J will be executing in the critical section, or the vice versa, or the other thing will happen, or the reverse thing will happen, right? So that ensures progress. That is, if no other process is there into the critical section, either process I or process J will get the turn to enter into the critical section, because turn variable can have only one value among I and J. So satisfying both the conditions for both the processes is impossible. One condition will be unsatisfied, that is the turn variable. Okay, so that ensures that one process will be executing in the critical section. So one process is selected in finite time, since there are finite number of lines that are written, finite number of codes that are written. So yeah, it ensures that in finite time we'll get to the critical section. No, both the processes will not continue in the critical in this line indefinitely, right? So yeah, that is what is ensured. And coming to the bounded wait problem, since there are only two processes, it is it is obviously satisfied that if one process is coming out of the critical section, the other process will get entry into the critical section always. So yeah, all the three conditions are actually satisfied by just the Peterson solution only. Okay. So yeah, but the problems with Peterson solution is that here, as you see in this line, the process that has to wait, it will be involved in busy wait. Like it will be there in the ready queue again and again, and it will be scheduled, and all the processes will happen, but it will just result in busy wait. So that is a problem. And another problem is that it just works with two variables. As I said, that you can assign the turn to just one another variable, so one another process. So that results in a problem. So these are the two problems that are related to the Peterson solution. So it solves the progress requirement obviously, and all other requirements. So A and B are the answers. Okay. Anyway, let's move on to the next question. So semaphore. Now we have come to semaphore. So semaphore is a dash used to solve the critical section problem. So what is a semaphore? Special program for a system, integer variable, hardware for a system, or none of the above? Okay. Anyone else would like to contribute? I got one answer. Anyone else would like to contribute? So in this session it is mostly theory. We will not have any numerical problems in this session like some of the previous ones. So yeah, it is mostly about logic and theory, about the synchronization part chapter of the operating systems. So yeah, anyway, let's get back to the question, and yeah, anyone else would like to contribute to the solution? Anyway, let's get to the answer then. Yes, it is an integer variable actually that is used to solve the critical section problem. So the following are hardware solution for the critical section problem. So till now we have been looking at some of the software solutions, that is Peterson solution and semaphore. Now what are the hardware solutions? So test and set, semaphore, lock and unlock, all of the above mentioned. So anyone would like to contribute that which among the following are hardware solution or solutions? There can be multiple answers also. So these solutions are dependent on hardware. There are special hardware requirements. So on the basis of that depends the success of the solution. So which do you think is correct? Which among the following do you think is correct? Anyone would like to contribute? Okay. Anyway, let's go to the answer. So test and set and lock and unlock are the hardware solutions. So what happens is that, so why are these hardware solutions, is that these are also actually variables. If you look at the solution, from the code point of view, but it requires special hardware such that the it requires special hardware such that the setting and resetting of the variables in the registers, they happen at a single time frame, right? So there is no interrupt between those hardware instructions, so that the setting and the resetting of the variables, like for example in case of lock and unlock, setting and resetting of the locks, they happen as a single instruction. There is a single hardware instruction. Okay, so that is where they require help of the hardware. The OS requires help of the hardware, and that is why these are hardware solutions. I'm not going into the detail of that. Let's move on to the next question. That is, the types of semaphores in the operating system are mutex and decimal, binary and counting, mutex and counting, binary and decimal. Okay, I immediately get one answer. Anyone else would like to contribute? So binary and counting is correct. So there are two types of semaphores actually. So what semaphore, I did not go into the details of semaphore. So what happens in semaphore is that there are two functions, wait and signal. So in wait, what happens is that you are waiting for a particular variable, and in signal what happens is that you are signaling you are feeing a particular semaphore. So semaphore is a variable, as I said in the previous slide. So integer variable. So what happens in counting, what happens in binary semaphore is that it can so the processes that wait for a particular variable, it can be just one. So it is in binary semaphore only one process gets entry into the critical section, but in counting semaphore there can be, since there is a variable, that integer variable can the count can go beyond one also. So in the counting semaphore there can be multiple variables that that can get entry into the critical section to perform a synchronized operation. Okay, so certain types of jobs that can be allowed. Okay, so in the bounded buffer problem, the empty and full semaphores count the number of empty and full buffers, or count the number of empty and full queues, or count the number of empty and full memory spaces, or none of the above. So which do you think is the correct answer among the following? Anyone would like to contribute? Okay. So we are asking about the bounded buffer problem. Okay, we are talking about the bounded buffer problem. So anyone would like to contribute? Okay. So yeah, the bounded buffer problem, as the name suggests, it's a bounded buffer. So yeah, the empty and full semaphores count the number of empty and full buffers, obviously. Okay, so how many buffers are full? So as you may have studied from the theory, as you may have got idea from the theory, that there is a producer process. So this bounded buffer problem happens in case of the happens in the case where there is a producer process and there is a consumer process. So the producer process produces something and the consumer process consumes it. Okay, it may seem similar to the read-write problem also of synchronization, but yeah, actually after consuming you do not get back that variable. Reading actually does not consume that variable, but yeah, you get that idea, right? So what happens is that in the producer consumer process, one process produces a variable, and suppose for example one process produces a solution to a function and the other process uses that same variable to override it with another variable. Okay, there is that case of overriding it with another solution. So yeah, that results in empty, and so that is what is the problem that is solved by the bounded buffer problem. So yeah, it has two buffers, that is counting the number of empty slots and the number of full slots, that is buffers. Okay, so I already said the answer. Anyway, would you like to contribute? The bounded buffer problem is also known as the reader-writer problem, producer-consumer problem, dining philosopher's problem, or all of the above. Anyone would like to contribute? So while you are attempting this problem, I would like to go back to some of the problems of semaphore. So you may have studied about deadlock and starvation. So there is another problem also of priority inversion. So I don't know if it was covered in class. So what happens in the case of priority inversion is that suppose there is a low priority process Pi, and there is a higher priority process Pj. So suppose the low priority process is already there in the critical section, and then the higher priority process Pj comes into play. So in a specific scheduling algorithm, that is the priority scheduling algorithm, only Pj can execute before Pi, right, since the priority of Pj is higher. But Pi already has entry into the critical section, and suppose that Pj also wants entry into the critical section. But since one process is already there in the critical section, so what it needs to do is it needs to wait outside. But since it has more priority, it cannot only Pj can execute first before ahead of Pi. Pi cannot execute before Pj. So that creates a deadlock. Okay. So what is the solution to that is the simplest solution to that is increasing the priority of process Pi, so that it is able to execute before the completion of execution of Pj, and in that way the problem can be solved. Okay, so that is the solution to the priority inversion problem that happens in semaphores. Anyway, let's get back to this problem. So the bounded buffer problem is also known as I had already said, it is the producer consumer problem. Anyway, this is the last question. So the dining philosopher problem will occur with 5 philosophers and 10 chopsticks, 5 philosophers and 5 chopsticks, 4 philosophers and 5 chopsticks, and 6 philosophers and 10 chopsticks. So I am not actually specifying the number, but you need to compare the numbers of number of philosophers and of chopsticks. So that is the question here. Anyone would like to contribute? Okay. Okay, let's get to the answer. So yes, it is 5 philosophers and 5 chopsticks. So this is the dining philosophers problem. Here what happens is that there are 5 philosophers sitting in the 5 tables. I have taken the example of 5. There can be multiple, more than 5 also, or less than 5 also. So as you can see, there are P0, P1, P2, P3 and P4. Okay, and there is a plate of noodles in between, in the middle of the table, and all the philosophers have plates in front of them. So what happens is that they are philosophers. They just sit there, think about something, and when they get hungry, they take noodles from the center into their plate, take the chopsticks, which are actually shown as forks here for some reason, and then they can have the noodles. Okay, so the problem is that there are just 5 chopsticks. So you can eat with 1 fork, but you need 2 chopsticks to have noodles, right? So yeah, think of these forks as chopsticks. So the forks actually solve the problem. You can what is the problem? What is the solution if instead of chopsticks there are forks? Can anyone write in the chat box? What is the solution? Since you just need 1 fork to go ahead to complete the problem, what is the solution if you have forks instead of chopsticks? So the solution is that it can either take the fork I plus 1 percentage 5, or it can the process can take the fork I minus 1 percentage 5, right? Either one is the solution. So what happens is that if it is I minus 1, it will take the left fork. It is I plus 1% 5, and it will take the right fork. Okay, so that is the solution. But in case of chopsticks, what happens is that they require 2. So that is the dining philosopher's problem. Okay, so yeah. So anyway, we have come to the end of the session. If you have any questions regarding any problem, otherwise I have a problem with me, which I did not want to include in this slides, but yeah, I will continue with that problem. Couldn't get that last question. Okay, so what I was asking is that suppose instead of chopsticks you have forks. So you just need 1 fork to have noodles, right? So in that case, what will be the solution? So what is the simplest solution? Does it require any semaphore? Does it require any critical section? Or what will be the software solution to the problem? So what I said is that since you require only one fork, so the process, so think of these as processes that require the resources of fork. So since there are 5 processes and 5 resources, so what it can do is it can either take the resource I minus 1 %5. So since there are 5 processes, I have to do %5 because it will come back to 0, right? Either you have to do I minus 1 %5 or you have to do I plus 1 %5. So I plus 1 %5 will signify this fork, considering this as fork 0, okay, and I minus 1 will signify this fork. So it can the process can either get this resource or it can get this resource. So if it gets so each of the processes will get the left resource if it is I minus 1 %5. So that way there will be no problem of deadlock and starvation, and each process can go on with the solution without any entry into the critical section, because there is actually no need of sharing any resource, because each process has its own individual resource, right? But if instead of forks you have chopsticks, what happens in that case? In that case there is a requirement of shared resource and shared variable. So in that case there comes the idea of critical section, there comes the problem of critical section, okay. I guess that was it. If you have any doubts, I can answer your questions. Otherwise, thank you all for joining the session. Hope to meet you in the next session, same time, same day. That is Tuesday 6 p.m. and maybe we'll have more problems to solve next session. Okay. Thank you all for joining, and drop off. And those who had joined in the previous section, that is week 6 solution, I had said that I will change the solution a bit to keep it more explanatory. So I haven't done that yet. I will update the slide, okay, in this week. So if you are interested, give it a go by the end of the week or so. So I'll change it by then. So you may remember the problem that we were discussing in the previous session. Anyway, the other things are done with, so you can just drop off. Thank you for joining. Bye bye.